We
We
can't hear
cannot
him
hear.
either.
Yeah, we cannot hear you. Hello?
He's not going to share the slides. They're not going to let us listen either.
I see. Okay. Perhaps we can send an email.
The chat should work.
Relevant to the development that we've done really over the last 12 years to make a scaled drone delivery system. I think the one difference is our drone delivery system is based on small UAS. So we're not flying people around. Our drones are, less than 55 pounds, a different risk profile than a UAM system. However, I think the underlying technology is basically the same. And right now we're at the point of doing thousands of deliveries per day to paying customers through hundreds of flight hours per day using an autonomy stack that touches upon each part of this ULI. So it's pretty cool. Great. So anyway, just a little bit about Wing. We were founded in 2012 within Google. And what we've been doing is building the preferred mode of delivery for millions of small packages. That's a key part, small packages, to be delivered every day around the world. So we're part of Google X alongside Waymo and Verily and Google Brain. But just a quick history. So in 2019 was a pretty pivotal year. That's when the FAA granted us a Part 135 air certificate for drone operations. That let us do beyond line of sight commercial operations as an exemption. Part 135 is the regulations that govern like charter operations. Like if you're going to charter a helicopter to bring you a lobster, it's kind of like the same regulatory framework. In 2022, we really started operations in Dallas, Fort Worth. And this was the first use of drone delivery in a major metro. In 2024, we established partnerships with Walmart and DoorDash, expanding service to even more places. And then last year, we announced the largest expansion in drone delivery, with plans to bring service to about 100 Walmart stores. And then just a few months ago, we announced an expansion of that agreement to expand to many major metros and 150 additional Walmart stores. So we do operate one of the largest aircraft fleets in the world right now. We're approaching almost 1,000 drones in operation any given day, and a pretty big footprint. And like I said before, we're partnered with Walmart, DoorDash, Avian, and the National Health Services in the UK. So our average delivery is like 5 minutes or less. About 2 million people have access to our drone delivery system right now. We've done 750,000 deliveries. And our fastest, we've done the most deliveries in 1 hour, which was a world record. We did that with DoorDash a few months ago. But anyway, the reason why I'm telling you all this is that believe that we're beyond the proof of concept part of drone delivery at this point, and we're well into the hockey stick scaling, if you will, of building a business around this. So there's partners that want our system, and there's customers that want our system, and it had been all enabled by this underlying autonomy technology that we've developed over the last decade. So just to get a little specific on areas that we fly in, Dallas-Fort Worth is our largest operating area. We operate in Houston, Charlotte, North Carolina, and Atlanta, Georgia. And pretty shortly, we'll be expanding to Tampa, Miami, Orlando, LA, St. Louis, which is pretty nearby, and Cincinnati. So at least a few months ago, we had 42 sites. I think we're up to 50 something sites right now. They're opening up every day. I actually can't really keep track of it anymore. But in 2027, we should be at about 270 locations, stretching from coast to coast, which is quite exciting. And so although we have these operations in the United States, we do have an operation in downtown London. And just to give you an idea, this isn't just suburban operations. I'll just let this video play behind, but this was an operation where we're flying between two hospitals in downtown London, moving blood samples from the test collection area over across town to another hospital that actually had the testing equipment. So before they had 2 trips a day where they would drive these samples across town. But with our system, we were able to fly basically these on-demand lab samples so they could get testing back really quickly. So apparently this supported scheduling surgeries a lot better and a lot more dynamic scheduling of procedures and whatnot. But I mean, this is like, no kidding, urban operations in some of the most complex airspace in the world. And the autonomy stack that we built really allowed us to do that. And so did the regulator in the UK, they agreed. But that gives you an idea of the operation. Cool. Right. But anyway, finally, there needs to be a fast and reliable, cost-effective delivery solution. And at this point, there's no sign of it slowing. So there's a pretty big growing value proposition. So traditional delivery methods are expensive, unreliable, and slow, particularly for these relatively small packages. This radical solution, which doesn't seem as radical anymore, is to just fly the packages straight to people. And then the breakthrough technology is really this autonomy stack that all of you have invested your careers in creating research that has enabled. So just quickly about the system to give you an idea, we operate from these charge pads that can be located anywhere. So they're pretty simple, just PCBs that you can put on the ground. The planes land on them and then charge. So there's no battery, there's no humans swapping batteries. The drone will take off and lower a little winch and a hook, and the loader can load the package onto the drone and it winches it up. And then the drone cruises en route to your house or wherever, and then delivers it at your designated delivery location. So here's like a top view of what one of our so-called nests look like. So when I talk about we have 50 locations, this is what they look like. Not a lot of infrastructure, just some pads and power and a fence. A little bit about the airplane. This is our main airplane that we're flying right now, but it carries 2.3 pounds of payload. Overall, the whole plane itself only weighs about 12 pounds, so it's pretty lightweight and small. You can just hold it. Cruises 58 miles per hour, and it has about a 6-mile delivery radius. We recently deployed a larger aircraft that carries twice as much payload, so it's a 5 pounds payload. And this aircraft weighs 17.2 pounds, but same cruising speed and same radius. So it's an example of a common avionics and autonomy architecture applying to multiple airplane types. We kind of view of having a library of different airplanes for different use cases. So in this case, we made one bigger because our partners wanted to carry more payload. It's entirely reasonable to make an even smaller airplane than we have today for other applications. Cool. And maybe just a little bit, I mean, this is the way that I think about the autonomy stack, and there's nothing really remarkable here, but you have inner loops with force and torque control, wrapped around that, attitude control, velocity control, position control, waypoint and path tracking, path planning. onboard decision-making, and flight area management. So, relevant observations of the flight area feedback into a geospatial and like model of your fleet. And then, fleet-wide optimization, which is controlling the airspace usage to maximize deliveries per minute. And we're definitely in the outer parts of this autonomy stack and even a couple loops beyond, which is quite exciting because we've reached that scale where there's business reasons to solve those problems at this point. But this should look pretty familiar to you. And in this ULI, there's research areas in each part of this autonomy stack, which has been pretty cool to see. And maybe just one note, because it's such a hot topic. Our philosophy is as you go up the autonomy stack, there's more and more need for AI and ML. And there's more relevance for those sort of more non-deterministic techniques the higher you go in the autonomy stack. We don't need an AI agent in our electronic speed control for our motors. It's just not worth it, although you could if you wanted to as an intellectual exercise. But where we see these AI techniques and AI models are higher in the autonomy stack. And then also one note, I would also say that verification and validation of these, and I'm preaching to the choir here, is really the tough problem actually. And we've found some pretty interesting use cases for AI and ML to aid engineers in doing validation and verification of very large scale simulations, finding tough test cases, not to be a replacement for critical thinking, but something to find things that you wouldn't have seen otherwise. That's another very key use case that we found. So yeah, those are just my quick notes. Didn't want to take up the whole time, but happy to answer any questions right now or afterwards. But really, it was an honor to be part of this ULI. I'm looking forward to staying connected with all of you. Just because this ULI, this particular one is concluding, that doesn't mean that we can't continue a relationship. And I'm interested in seeing all the research that you and your students are doing, and looking forward to future collaborations. So, yep, cool, yep.
I have a question to ask.
Yeah,
If I may.
yeah.
So this is Evangelos though. Very nice.
Supervising.
Yeah, like our system is designed for a one to area concept of operations. I think we're working through that with the FAA right now. I think our approval is up to 1 to 80, so 1 pilot to 80 airplanes. So it's effectively one to area. Kind of how that works is you have to actually demonstrate in the real world those ratios. So it's like as we've achieved these operational scales of actually flying 80 airplanes in one flight area, the FAA sees that it works okay, and then we get signed off. So we've just been building up the ratio over time.
The second one, sorry, just follow
Yeah.
up. From what you said about using AI to do validation verification, well, help that, right?
Yeah.
Are you using that in an adversarial sense, in the sense that, hey, find where I break in my step?
Yeah, for sure. We've done experiments with doing iterations on test cases. So you set a sim scenario, run the sim, look at the data, have the AI agent look at it, and then revise the sim input. Some pretty interesting results there. And I think also the data analysis, like the data analysis abilities of specifically Gemini, because we're an Alphabet company, is pretty remarkable. And really lowers the bar for you to do data analysis at a rate that you couldn't do before, and to try things out and look in corners of the data. So it's another area. And that stuff is available to everybody, through all the different AI companies. So,
Thank you.
yep.
So I have,
Before seagulls realized they could get fries from your.
There have been a handful of situations where birds have interacted with us. There was one notable one. It happened in Australia where a raven grabbed a tail of our airplane, and someone got it on video, and it showed up on the news. Our good old robust control and gain and phase margins, were robust. We didn't have a Raven detector on the plane, but it worked out okay. But, overall, I think we haven't really had that much of a kind of a impact of wildlife, any more than maybe a car driving down the road and squirrels and things like that. But yeah.
Can I?
Enunciate, and the human should look at something, or how does that operator observe?
Yeah, good question. The one control that the operators have is the ability to draw a flight restriction in the flight area, and then airplanes will not fly in that area anymore. And then if there's any airplanes within that area, depending on the sort of geometry and situation, they might execute a contingency landing. So that's kind of it. So if someone calls up on the phone, like the local police, and they're like, hey, I don't want you to fly in this area anymore, they'll like draw a flight restriction. But there's not really any actions when there's nothing where the airplanes enunciate and the pilots have to take an action based on that specific airplane. We've designed that level of control out of the system because it's not practical, because you could have all 80 kind of enunciate something and then they can't do anything. So that's what I should have said. Yeah. Management by exception. Cool. Was there a question?
Can I ask one question from online?
Yep.
Yeah, very nice talk. And what you said at the very end, that you see more the use of ML as you go higher in the autonomy stack. So I'm guessing what you mean there, and I just wanted to confirm that with you, is that as you go into looking into this problem more as a supply demand system, as a network flow control problem, right? You really need more ML models in a way that allow you to handle the complexity of the operation or the scale of the operation.
Yeah, I think that's one way to frame it. And maybe what also I was trying to say is that I believe that once you get higher into that autonomy stack, even beyond what I presented on the slide, there isn't a classical method that exists to address that problem. So then it drives you towards those other techniques. And it's really a generalization that what we have tended to use AI and ML, it's been higher in the autonomy stack. So, yeah.
And one last question is, how important is capacity planning at that point, right? Because now, I mean, you guys operate only like 1,000 only. Like that's an amazing number too. It's already a big number, but in like 5-10 years from now, this number can be times 10, times 100. How important is capacity planning?
It's extremely important. I mean, I just remember, 10 years ago, we were just trying to get one drone to fly like once. And we kind of dreamt of the day when that would be the challenge, right? Like, where do you allocate the airplanes that can carry more payload versus the airplanes that can carry less payload? And it does become a network planning and logistics problem. And we're at that stage where we have to start doing that. Or I shouldn't say have to, but that sort of work of network planning. We have a whole team called the Delivery Network System that does this. That does this sort of capacity planning and real-time network optimization. We're at the stage where we can make a meaningful movement in the business on that technology. We're 8 years ago, that wasn't the problem to solve, but now it is. So much like how the airlines might have to plan what airplane types go to which airports, it's like the same exact type of stuff. So it's pretty exciting.
Thank you.
Yep.
Thank you, Bankus. Thank you, Brandon. So now we are giving Now we're giving the stage to our students and postdocs who have, as I said, research very interesting in the autonomy space, yet not covered by the ULI. It's relevant. It came out from our other sponsored research programs with NSF, with the Air Force and other DoD programs. We decided to give them the opportunity to present here. So this is not funded by ULI, but very relevant. So I think you take over.
Right, so hello everyone, I'm ULI. I'm one of the PhD students from Naro's group, and I'm working on an omnidirectional multirotors that sort of trying to expand the application of the aerial vehicles. So to give you guys more context of it, so as you all know, for the conventional multirotors, they already like been doing a great job, but they are still having this under-actuated dynamics, which means that for the platform to move left or right or forward or backward, they need to tilt their platform first. So typically it's fine, but when it comes to certain applications, for example, if you're doing a contact-based inspection with those kind of a inspection knob at the front, you don't want those kind of a detector to move up and down while moving the platform. So that's why we came on with the this platform that can fly with the that has the omnidirectional flight capability, and it has 8 rotors with the 14-inch cube shape. The mass of the platform is around 1 kilogram, and it can hold up to 2.5 kilogram. Also, I built the custom-built PX4 that controls the whole architecture. Oh shit! Sorry. Second. So as you can see here, using the hardware and the proposed hardware and my custom-built flight controller, I was able to demonstrate the omnidirectional position tracking. So at left, although it's tracking the trajectory quite fast, the platform barely tilts because it doesn't require the platform to tilt to move horizontally. Also for the omnidirectional hovering case, unlike the quadrature that if the platform tilts, it have to fly away. But for our platform, since thanks to the omnidirectional capability, it can stay at the same hovering point while rotating in many directions. Oh, by the way, for more details, I'm gonna have the poster session. So if you have more questions, please visit by my poster session. And by expanding my controller with the L1 adaptive controller, we were able to show the stable hovering with the fan disturbance, which is quite strong. And even going further, we've shown this high precision flight inside the narrow space, which generates some strong disturbance. But as you can see from the orthogonal view, the platform is like barely moving thanks to the L1 adaptive controller capability. And I think it gets more fun at this point. So utilizing this capability of the stableness and agility of the platform, I'm trying to expand the platform as a general aerial manipulator. That, for example, at left, you can see that the platform is tracking my hand motion, which enables a teleoperated system. And also there are some actuators that, for example, for now, it has the cleaning squeegee to clean the whiteboard. So using this capability, I was able to show the teleoperated cleaning on a vertical surface of the whiteboard. So you can see that with some kind of a controller with the L1, I was able to done this task very well. And it's quite similar. So, and then now I attached the board marker to the system and then was able to show the teleoperated vertical surface writing. So with the same controller, it can deal with the frictions And it can also there are some disturbance from the cable, but with the L1 and the context-based controller, I was able to do the teleoperated writing without a problem. And I think this is kind of like a highlight for our platform. So even expanding the platform further, I made the whole system autonomous, not just a teleoperated system. And also to make the system more challenging, I also put a strong fan on it, which generates around like 12 miles per hour wind. Also to highlight the omnidirectional capability, we've done the task on the inclined surface of the whiteboard instead of just a vertical surface. And at the left top corner, you can see that how the platform behaves for the given target trajectory. And at the left down, you can see how the first person view of the system looks like. So it's writing a Skyframe, which is one of our project name. So you can see that although there are strong disturbance from the tether and also the fan, it was able to do the task very successfully without any issue. And to even expand further, we attached the Reaper to the platform. So our idea here is that we don't want to have just some kind of surface measurement system, but we wanted to kind of more like expand the concept of the humanoids doing this dexterous manipulation to replace the human work on the ground. But we wanted to kind of be like humanoids' hands that flies on the heights and then do the job instead of that kind of doing jobs for a human. So for that direction, we attached the gripper, and I was able to do the pick and place with the teleoperation manner. So there is me behind trying to like locate the water bottle that's moving because of the downwash. But thanks to L1 adaptive control with the disturbance from the water bottle and also the tether, I was able to do the teleoperation without an issue. And this is my personal favorite experiment. So some people may think it's sort of crazy, but I really wanted to maximize the agility of the system and see badminton playing multi-rotor. So I tried to minimize the latency as possible for the whole system. And as you can see, the platform kind of tracks my behavior almost like in real time. So this kind of like was to prove the agility of the platform, and we were trying to make the whole system autonomous, because in the end we want to see the autonomously playing badminton multi-rotor. So those are some of our efforts. So basically, I made a digital twin of the given system, which is a hardware, controller, motion planner in the NVIDIA Isaac Sim. And using this digital twin, we are able to, it's on the way, but we are currently trying the optimal shortcoding strategy using the reinforcement learning. And the reason we are not using the imitation learning is that we are optimized to play the badminton with the human body, but we wanted to see that what would be the best policy for the drones, this platform, to play the badminton. So that's some of the direction that I'm working on to make this kind of a new concept of the beyond the typical aerial vehicle. So that's it for the presentation. Thanks for listening, and please feel free to ask any questions. Please.
When you're training, is that in 2D or is that in 3D?
Everything is in 3D.
Okay.
Everything is in 3D. So at this stage, there are a lot of parameters to tune, like a cost function and all the things. But yeah, in the end, we are trying to find the best policy and try to deploy to the actual system to have the physical AI. to the real system.
So what I'm hearing is that when Mike finally has that competition for BAM, this is a prime.
Yeah, maybe we can make the, oh yeah, we can play the baseball playing, the heating, the module chart. That'd be awesome. Right.
I have another question regarding this badminton play or other previous drawing tasks you done. Do you use field perception side? Do you use onboard perception or use criminal constraint just providing conscious information?
So that's
Control tasks.
That's a great question. So for at this stage, like everything going on here is some kind of like new concept. So for now, I'm more like on a stage of proving if like this controller and hardware is actually possible. So basically, what I'm using is everything is based on the motion capture. But in the future, if I can prove the concept using the hardware and the controller, probably I can expand to more like an onboard vision sensor and maybe play the badminton outside. Thank you. Yes, please go ahead.
A question about your IZ-based simulation training. Do you consider at all the aerodynamic side effects of having the blowing of the multi-rotor propellers into the badminton ball and its trajectory?
Yeah, so that's a great question. So that's something it's really hard to model, but I've done some kind of preliminary experiments of heating the badminton shuttlecock, and it seems like since the badminton shuttlecock is like coming very quick and there are not much time to interact, it seems like that there should be some kind of disturbance, but it seems like it was kind of negligible. Right, yeah.
And since you mentioned that you're trying to capture like non-conventional ways of hitting the ball, are you penalizing any contact with the body of the motor, or are you only assuming that the only right way to hit it is with the paddle? Or are you just letting anything happen and just avoiding?
Can you kind of like give I was a little confused about what do you mean by which one you penalize?
Like, are you trying to make the ball return in any possible way?
Oh, I see.
Have to hit the paddle?
That's a great question. So basically it depends on like what kind of situation that I'm gonna be that I'm gonna make the platform optimized. For now, it's more like focusing on just hitting the ball.
Yeah.
So that's why it's kind of like dropping, like shooting it down. But in the future, we are trying to make it more like an hitting to the specific point. And maybe you can kind of design like an optimal badminton playing strategy for the platform. Thank you. All right, it seems like that's it. So let's move on to the next presenter. Thank you very much.
Okay, I was trying to fix that. Sorry, it's all good. Good. And then here it is. And then here. That's fine. That's really fine. You got the Teams meeting. Where did it go? Double click on this double face right here. Okay, perfect. Share. Mic mode, and then share autonomy. And then just delete the date. Oh, okay. 040554. Perfect. Okay, perfect. Okay.
Okay. Hi, everyone. I'm Sandeep Manik. I'm a postdoc working with NARA since 2024. And this is a work on shared autonomy, basically from robots to AI agents. And this basically at a decision level and not much lower in the control loop. So this is more on the work on human envelope. So we are interested in autonomy. We are interested in autonomous systems, and this is quite visible in some of the self-driving cars over here, some of the flight control systems, and more towards unitary and robotic applications. But ever so often, what happens is that these systems encounter some sort of scenario which they cannot handle, and an expert needs to intervene and control the system in order to bring it back to stability or bring back to a situation which is more safe and feasible. So you can imagine this as a switching between these two systems, which is the expert and the agent. And the idea is to incorporate costs of humans, which is this cognition cost, and the agent, which has this sense of cost. And this takes into the system, or else you can imagine that one of the entities will be controlling the system all the time. The other thing what we want to account in this situation is the human asymmetry. Basically, the human has a higher authority when it is operating a shared system. That is, you will enable when you will switch on the cruise control. You will also control when to switch it off. That's like a semi-autonomous system. And the human has a higher authority of override. The agent can only switch when it is allowed. The agent can indicate when it is ready. So with that, you can imagine that these systems will behave differently under an expert and under an agent. So you can imagine this as a binary state, which is A is for the agent and H is for the human, which is 1 or 0. We call that the flip dying state. And the rules of this game, you can think so-called of a game. Imagine that you're starting with the autonomous agent, and it requests the human to take over, right? But the human is idle, like we are lazy and we do not want to take over the system. So the system remains in control of the agent. Next, what happens is that the human override occurs. The agent is not yet ready, but the human can take control back of the system. Now the human is idle, the agent is ready, but it does not want to switch it back. And the switch back only occurs when both the agent is ready and the human is also ready to give it back to the agent. Now, this can be incorporated as an if-else statement. And what we want to do is basically also account this in solving when to switch between human or agent. We accommodate this intent of the human, which is like this stochastic intent, which is trust into the system. There is a likelihood of trust to an AI agent. There's a likelihood that you will switch it on. There is also situations where the cruise control is working fine, but you deem it's not good enough and you take back control. That's like sort of an intent which we say here. Now the objective is as typical objectives of control systems go. You have a terminal state cost. You also have the state cost, which is for some finite horizon L. And then you have takeover costs. There are also costs in takeover, such as the cognition cost, which I mentioned before. So now the key question is, when should a human or an agent take over? Right? It turns out that we can use the framework of backward recursion and game theory in order to solve this game. We say this is an identical interest game. And the way it works is that you have the value at a given state, and this is the alpha, which is either the autonomous agent or the human. And then there is the future cost, right? The future cost is actually solution of this 2x2 game. It's just between idle or takeover. And then each of these entries will set this value of either an AI agent or an agent, or the value of what the human considers the system to be. And in the spirit of all control theorists, we just do this on the linear system and see if we can get closed form solutions, and we do. And it turns out there's a very simple switching strategy between the human and the AI. Consider the system to be under the human, then it will be idle, that it will retain control if the value between them is less than the combined costs, which is the costs of cognition and sensor, and it will take over otherwise. Similarly, you have such simple rules even under an autonomous system where it compares the values, it compares the cost and something called as the intent. And this is one of the scenarios or the simulations of a vehicle which is trying to go straight, encounters an intersection and then takes a left turn. And you can see that there are regions in which it is better for the autonomous agent, the human agent to operate. So in here, the human is saying that I will retain control, and the autonomous agent is saying, please take back control, human. You will do a better job here. But in the turn, which is in this curved segment, it actually is better for the agent to take control of the system, and the human also responds in a similar way. So this also has been extended and tested in nonlinear systems, like the classic mountain car example. And this is like the profile of what the human autonomy switching looks like. But the more interesting question is, we are thinking this of a framework, which is this system which sits here, and to extend this to non-linear settings or settings where we get data from, and we want to understand and fit this value of what the human is versus what the value of an agent is. And communicate back to the user basically through some of these tools, which is very natural language based. And moving forward, we are also looking into systems that if you replace this autonomous system, let's say with speech, or you can imagine conversation as dynamics conversing between you and the AI or the agent. And there are parts in which the human needs to intervene. And this will be very useful when you have critical or sensitive information, such as financial or medical information. And this framework basically allows you to exactly say that when should the human intervene and when should let the autonomous agent run free, right? Yeah, that's pretty much it. It was just a quick one. I also have a poster and a demo if you guys want to play between an AI and yourself to achieve a common goal. Yeah, I'll see you in the poster. Oops.
You should meet that one. So great work, really relevant problem. Let me give you the next step that I think you guys need to look at. There are circumstances where a human cannot take precedence over the agent.
Right.
Whether it is a malicious intent or incapacitation, I'm thinking like the airlines, right?
Mm-hmm.
So how do you add that contingency in your decision making? Clearly, it needs to be something that, no kidding, makes a determination that the human is going to end up doing harm to the system.
Right.
That's a different conversation. And maybe, how do you incorporate that and how do you start thinking about it within this framework?
So great question. So in that situation, when we are looking non-cooperative setting, this matrix which you see, identical interest, becomes non-zero sum. So adversarial in nature, and you can imagine this to use to train a pilot. Basically, you're encountering or reasoning about the worst case decisions what the pilot will take, and under that, is it safe to transfer to the trainee pilot, or is it better to keep it with the autonomous system which will perform it?
I'm going one step further.
Okay.
I'm going to where the pilot might be in control, but the underlying agent determines that pilot's actions are detrimental and will actually take away control. Not the fact that the control will be transferred, or keep control, but actually take control away from a human.
Okay, that needs to be baked in, because in here we made an assumption that the human has higher authority. That can be changed, by the way. Based on the entries of it, it will shuffle around, and then it will become that the AI or the agent has potentially a higher authority, and not only just to signal what I'll show you in the demo, but also to actually take over from the pilot.
So where I'm suggesting, where I'm heading with this is that, yes, this framework can handle that.
Yes.
But you may want to start considering adding other technologies that will help you determine when that case is to be engaged.
Yeah, that's correct.
This is really not an easy problem, but I think it is going to be a very important problem.
Yeah, okay. Thank you so much.
All right, so the table's not quite done.
Okay.
Situational awareness,
Mhm.
so, in the human aviation, right, like switching between pilots, who has SA, who doesn't. So how do you infuse that in this structure, right? So how do I know that how can I responsibly transfer authority to the agent? How do I get insight that it has SA? It sees that pedestrian.
Yeah.
It sees the same traffic. It realizes that, hey, the right motor has failed and the temperature sensor's been bad for the last half hour, right? Like, how do I infuse that knowledge that you have SA and I have SA so that we can transfer safely, right? So it's a tough, I don't expect you to answer it, I'm just saying, like, that's, how do you weave that in, is gonna be important.
Yeah, perfect. That's a great question, actually. So the whole point of why this all works is if you can predict what the value under an agent versus the value under human is, if you can say that perfectly well, then you can do this, right? That is a very critical question. And that is very hard to do in scenarios like the autonomous driving scenarios. The idea in here is that the framework remains the same, but the key now is, okay, what are these values? What do I need to plug in? One of the possibilities is to use the data, what we collect, and to figure out what these values are. That's where we are heading in the learning. The other is to use something like Aditya's work on distributionally robust adaptive control to be incorporated in this under when the AI will be operating, figure out the worst case scenario, and then the human will be just based on data because we cannot figure out what the human mind is capable of. That is one of the possibilities which we can think of.
But another way to think of that would be at turnover time, there's some sort of information exchange, right? So like, the agent would have to tell me what it considers the most, critical or unsafe aspects at this time, right? And if it's missing one,
Yeah,
I can tap and go, hey, you're missing this person.
yeah.
Right? Or vice versa, right?
Yeah, that's another factor that you can imagine the information exchange, what the agent missed in its vision or its perception system can be somehow communicated back in a representation which it can understand, right? That's another, but yeah, great suggestion. I think that's all. Yeah, let's move to the next table.
Okay, next we have. Okay, perfect. Yeah. Sorry, just let me quickly figure this out again. Yep, now it should show up. Yeah, right here. Okay, and then I think Command L. Oh, we just did it.
Okay. Next we have Ishika. Ishika is a graduate student at UIUC, and she'll present some of the current things that she's working on. Go ahead, Ishika.
Okay.
Let me quickly look.
Okay.
Yes, that works.
Yeah, sorry. Yeah, hi everyone. I'm Ishika. I'm a third semester graduate student with Professor Naira. And today I'll be talking about our work on a robust task level control architecture for learned dynamical systems. So, sorry. Yeah, so if we want to deploy robots for complicated tasks like assembly, cleaning, servicing, or sample collection in like planetary robotics, we need them to perform these intricate multi-step motions, which can be difficult to hand specify. So to solve this problem, learning from demonstrations has emerged as a field that enables robots to learn or acquire skills from expert demonstrations, either through like kinesthetic teaching, which is like dragging a robot around and showing it how to do a task, or teleoperation, as Hyung Yu showed in his slides. One such method of encoding skills is to encode skills as an autonomous dynamical system, which is this differential equation, using a task space state. So in the field of manipulators, an example would be the pose of your end effector of your robotic arm. So instead of learning the dynamics of your robot joints, etc., you can just focus on your end effector and learn these sort of vector fields from demonstrations by an expert. For example, the red lines shown here. So now, given a bunch of demonstrations, you can fit a model f theta and roll out this differential equation in order to generate trajectories that the robot's low-level controller can be asked to track. Now, the problem with this is that, or the field of manipulators and how they think about this, the gap that they don't address is that even though you learn this f theta, you learn it in a disturbance-free and like an ideal setting, but you can have sensing delays or communication latency or unmodeled low-level dynamics or persistent external disturbances that prevent your arm from executing that desired end effector pose at every point in time. And there have been certain approaches to solve this. For example, this approach of stable dynamical system learning, which focuses on point A to point B tasks, like moving an object from point A to point B. So there is a single goal or target attractive state. And the way they do this is that they constrain the parameters of your f theta in a way that ensures convergence to a goal state. But they don't have such approaches for general trajectory-based tasks like piping a surface, turning a pot, etc. And to address that, some people suggest augmenting a virtual control input based on control Lyapunov functions or control barrier functions in the case of disturbances, which works if your disturbance is sort of impulsive or like suddenly appearing. So for example, if your robot's end effector is traversing this path and it gets pushed off course, you want it to come back and follow the trajectory. But in the case of persistent disturbances, this might not suffice, as we will see in our experiments. Then there are other approaches that sort of try to make the learned vector field attractive towards the trajectory by constraining their parameters. But these methods at the current moment require hand specification of these regions of attraction, and they also are limited to single goal tasks. So what we propose is like a task level wrapper around any learned f theta, and we don't require access to like a low level plant model or any hand specified regions. So mathematically, our control objective is to design a task level command such that our executed state remains in a tube around our desired nominal trajectory. And how we do this is to augment L1 adaptive control at this task-based level, along with a nominal stabilizing controller, which can be anything, but for our experiments, we used a control Lyapunov function-based quadratic program. And this UNorm needs to decide which point in the trajectory it needs to track at every point in time. And that is provided by this DTW-based target point selector. A little bit in more detail. So as we saw here, that although our f theta parameters can be constrained to like a single target point, we don't have anything that pushes it towards the trajectory. And to do that, we augment this CLF-based virtual control input and solve this quadratic program at every point in time. Our second component is this dynamic time warping-based target point selector. So just in brief, dynamic time warping is from like the world of speech processing, and it tells you how to measure the similarity between two time series or two sequences that may vary in speed or timing. So theoretically, you could use something like root mean square error to find which point of our executed trajectory corresponds to our target trajectory. But if the sequences vary in speed, for example, there is some delay here, we might not be able to perform as fast. So we
Oh, interesting. That is not good. Stop sharing, reshare. Oh, no. Oh, skip. What did I do? Share.
You didn't share.
Yeah, I accidentally clicked the wrong thing. Hopefully they should show up. Okay. And yeah, go ahead. I guess this should work now. Please.
Yeah. So what we proposed is like an algorithm that looks at the history of our executed state and looks at our target trajectory rolled out from our learned model and decides which point along that trajectory to track at every point in time, based on the DTW similarity between these two time sequences. The third is our L1 adaptive control, which has the three components: the state predictor, the piecewise constant adaptation law, and as well as the low pass filter. So we model all of the sensing delays or any unmodeled low level disturbances as this sigma z, which is the task execution mismatch, which is what L1 tries to compensate for. Now, not going into too much detail, but based on these certain assumptions, such as the bounded disturbance as well as locally lifted-ness of our model, we're able to derive this uniform ultimate bound on our trajectories. Now, in terms of seeing this working, we tested it out on these handwriting data sets, which is basically demonstrations of writing certain letters. And we compared our nominal f theta, which is just the learned model of the demonstrations. Then we augmented our f theta with the virtual control, stabilizing control, which is the CLF. And then we also compared it to our post complete architecture. And we tested two regimes. One is perfect, where we assume that our low-level controller is always able to track our task-level command. And the second is imperfect, where we have a double integrator low-level plant with a PID controller, and we inject matched and unmatched uncertainties into the low-level system. And to see to quantitatively see the improvements, we report the DTW distances between the executed and the target trajectories. So qualitatively, this looks sort of like this. For example, in this letter A writing tasks, if there are persistent disturbances and our nominal f theta, which is just based on our demonstrations, is shown by this dotted gray line, it might not be able to even converge to our goal point. And even though we augment CLF, we still aren't able to perform well. But with L1, we're able to achieve our task of following the trajectory closely and in a guaranteed manner. And quantitatively, we see almost like 5 times improvement with our architecture compared to other methods. And our windowed DTW-based target point selection also outperforms previous work on least effort-based target point selection. And yeah, we have also tested it. So these results were based on a neural ODE model for f theta. We tested it on a Gaussian process or like a Gaussian mixture model based f theta as well. And we see same improvement. So our architecture is not bound by our choice of f theta. It can be applied to anything. And right now we're trying to extend this to actual hardware. And before we go there, we are trying to work with higher dimensional spaces like a quad rotor. And for example, if we have this rising circle sort of trajectory and we inject unmatched, basically disturbances in the XY direction at some duration of our flight, we see that our green line, which is the the quad rotor's actual state, diverges from the intended blue line, which is the target trajectory. But with our architecture, it's able to closely follow that. And there's a lot of questions remaining to be answered, like what is good data and like how much data do we need? And also, where does this DTW break? Is there a time delay that causes things to not work? Apart from that, we also want to test out our architecture in higher dimensional task spaces and hardware like manipulators such as HumeGules or other build in robustness to errors in the learned dynamic system model F theta, as well as automate the process of selecting the window parameters for a TTW-based algorithm. But yeah, that was about our architecture. Happy to take any questions.
End of the day, everyone gets tired.
Yeah.
Right, so we're two more presentations, come show your two demos. And the legal is being slowly into this world, kind of wrapped it up. And with your goals.
Yeah, just like wow. Okay, just a second. Share window. This. And then it should be up.
All right, okay. Now we have Gene. Gene is a PhD student, again, working with Naira, and he has some cool robotics demos that he's going to show you.
All right. Thank you so much for this opportunity to let me show some of my works in front of like so many talented and pros. So I bring my two buddies here. So if you guys want to check it out, feel free to do so. It's all from scratch, hand built. I love them. They finished like too many cool demos with me. I basically today gonna talk about like two of my works recently. The one is the grass-based anchoring, the expanding urban perching as with a hybrid gripper for aerial robots. So that is kind of like the motivation, which is like the perching actually save the energy for your platform, and the grasping can let the platform do some like physical interactions. But few solutions can actually achieve both. And the existing solutions, it is like require the system to have some like specific perching tools or some specific perching surfaces or geometry. We don't want that. We want to let our the platform to perch on some really strange or irregular surfaces, something like a lamppost or a stop sign. So that is basically our like the structures. So we got like soft grippers. It can basically grasp like that, and that is a kind of like layout for our hybrid grippers. So we adopt like a foundation pose, which is kind of like a foundation model that can let us to throw the CAD model in and give us the world space XYZ coordinates, and then we use like specific coordinates to generate like a smooth trajectory. Let the L1 let the geometric controls augment with L1 to track that trajectory, and then after the drone is hover above the landing target. You see this kind of like a picture right here. It's like there's like a down-facing coaxial cameras that can let you do some like visual surveilling to make sure your target is always in your eye set. So that is like the first demo, which is we let the target to take several poles. So the foundation pole is actually capture the coordinate for the target landing pole, and after a while, the drone powers above the landing pole, and then the So I got a little buddy right here. So that is a kind of like the soft gripper right here. It can close like that. So it actually can adopt like different geometries. And we show this graphic here. Never mind. So actually the boxes here like see some like great demos, or we give some like sprint demos, which is like the quadrants are capable of like keep to grasp like batteries, marbles. We can actually watch again. Umbrella, friends, and this kind of like puzzle with your water bottles. And thanks to L1, all the trajectory are making pretty well, and we can do the stuff on target. Yeah. And for the next experiment, which is like the most exciting one, which is like the drone can actually grasp the adapter and then land on the stop sign. Which is basically use the same logic as before. The drone identify the target and then go hover above it, do visual circling, gradually touch down, grasp, and then re-take off, do the similar stuff, fly above the stop sign, and then land on it. So normally the drone cannot like really perch on those kind of like irregular surfaces or like those kind of like abnormal planes. But in this case, the drone can actually grab to the grass well perching pad, then it can like land on those kind of like stops and ends. So like for the future work, we're probably gonna implement some like vision language model to let the drone to decide whether that is like a perchable site, whether I need to grasp something to land on this, and also like we're gonna do some like cool demo in real like the outdoor scenarios. So basically that is like my first works. Then my next thing is like this throw maneuver, which is like exact trajectory for invariant target hitting. Anyway. So like throwing robots like exploit gravity to deliver objects, but the existing solution is really determined by the time. So just like for example, you want to throw like an iCard over there. There's like only like one singleton of time you can throw the stuff and it land on the target. But we really don't want this kind of stuff happening. So which is that we develop this throw maneuver, which is like a carrier trajectory that guarantees target hits like regardless of the releasing time. Inspired by the last year California wildfires, since like if you remember, there's like a giant plane spread those kind of like fire extinguisher chemicals all the way. It is that kind of like chemical inefficient. It is time inefficient. So if we can throw like a bunch of like chemical extinguisher ball on target precisely, regardless of time, that would be pretty good. So that is kind of like a throw maneuver derivations, which is that we start from like a governing equation of a free fall projectiles with a carrier release the object at like specific location and a velocity that is like yield the target hits, and then we differentiate it with respect to the throw time, and then we can get like those kind of like governing ODEs of the throw maneuvers. The detailed derivation gonna be in my paper ACRL 2026, so feel free to check it out. So I got some like simulation results. We basically have like three kind of like trajectories, which is like predefined vertical motions. The objects are released from the maneuver following a dash projectile, and they can always hit the targets. And we got like some outdoor experiment. So that is like a single throw. The drone can with this type of gripper can grasp like one golf ball at a time. And to throw the stuff on the target. So that is kind of like the results. We repeat the throw for like 10 times under different spatial configurations. Through maneuvers can actually achieve like smaller mean error and CP90 than the constant velocity throw, and also the tube acceleration zone, which is like our strong baseline, showing like a better accuracy. And we also tried this kind of like a batch throw, which is like contains like this kind of like crank slider lock release magazines, which can contain like 5 golf balls throw at a time, and we achieve similar results. Which is like we beat our baseline, which is like hover throw, constant velocity throw, and the tube acceleration baseline. That is most interesting result, which is like the sequential throw. We use this kind of like dual hopper with servo-driven rotational sector gate to launch 14 golf ball at a time. If that is like not clear, we have like a really cool demo at a night. So we use those kind of like luminous in dark balls, and you can see the trajectory And we can go one again. So the part we gotta start with right here. So that is the result. So since like the tube acceleration method does not really guarantee in this kind of like 10 seconds time interval, so we only can compare with the Harbor throw. Although the CP90 is like a little bit bad, but like we still achieve like a better like the mean error and those kind of like the throw maneuver is like kind of the this kinetic natures makes it like a favorable option for this kind of like time invariant throw, which is like kind of like choice for application like wildland firefighting. So yeah, that basically concludes today's my talks. If you got any questions, let me know. I'm gonna have like a poster section over there, which is like the green poster over there. I can show you the design for the drones. Let me know if you got any questions.
So you can throw the ball that he hits.
Okay, so I think this brings us to the last presentation of the day, and we have Siddhant. Siddhant is an undergraduate student here at UIUC. So he will present some of the research that he's doing, and it's interesting work on 3D graph reconstruction. So let's hear what Siddhant has to say.
Okay, window. And then there it is. Okay, and I go here.
All right. Okay. Hello, everyone. I'll keep it quick. So my work is on 3D semantic scene graph. It's a pipeline for certifiable UAV autonomy. And my work in this was mainly on creating that 3D scene graph in real time for downstream planning and LLM use by agents for better control and for more smarter drone systems. So the main problem is that currently with most existing algorithms, the UAVs can reason about obstacles and the landmarks and the characteristics of what they're seeing, but they often lack the semantic context that's required. So the semantic information that a 3D scene graph gives allows a human to reason with it in a natural language and for the UAV to distinguish, say, a wall from a door, and that influences the design and planning decisions downstream. So combining the geometry and the semantics creates a layered scene graph, which is shown here, where basically you have, say, the rooms of a building, which then go into, say, the tables and the desks in those rooms, and then the objects on top of those desks. So it allows for more adaptive and more semantic understanding of the place and also better commands that can be executed as well. So the pipeline is quite simple. We basically used a ROS system in ROS2 Jazzy. We ran a Turtlebot 3 robot in a gazebo world. And we basically mapped the topics. So the RGB depth camera, the LiDAR, IMU, and the stereo camera streams as well. And we basically created a sensor bridge that then would resolve all the TF frames and odometry, as well as standardize all of the sensor streams into the format that Hydra uses to create the 3D scene graph. And then Hydra would fuse these sensor streams into the truncated signal distance field integration, which is basically a 3D mesh reconstruction only up to a certain X distance that the robot can see. And it would also extract the places that it gets, all the objects, and it also create the agent map. From there, it would finally create the scene graph, which contains objects, rooms, edges, and spatial understanding of the area that the robot is supervising. From there, the scene graph can then be used by downstream planner and LLM algorithms with an agentic AI to query and to perform tasks. So most of my technical contribution in this was just making it work in real time. So I just remapped a lot of the sensor topics across the different architectures. And especially ROS, which was the worst one to work with. And we just, a lot of it was resolving the TF frame inconsistencies. And also we built a custom mapping node that would take the stereo and depth bridge and then remap that into the format that Hydra uses at a fast enough pace that it can actually construct the mesh. And the resultant impact of this was that we now have Hydra working in real time on a simulation software. And down the line, LLM task planners can now consume these scene graph objects and use and query them and generate motion level goals completely semantically in a natural language. And the full pipeline is reproducible on new hardware as well. And the semantic layers enable reasoning over like object types, rooms, which can be used for search and rescue, and for better planning in dense urban environments. And this is the demo of that working. So the R0 is basically the agent that the robot thinks it is. And then you'll see it trying to reconstruct the map, and that is the scene graph being formed. The R1 is a new place it has discovered. And so it's unsure if it's discovered it or not, but that is basically the pipeline. Thank you, and I'll take questions.
Questions?
Probably into like looping the, so right now we have the gazebo world truth that is giving the odometry. So now we want to loop it back and make it queryable with a LLM. And what we want to do is we want to make this integrated with the actual 3D capabilities of the robot itself. So if you can imagine, if the scene graph says a path is possible, but the robot needs to confirm that it can actually do that in the real physical world. So that's where we're going to go.
So the time has come to wrap up the day because our online participants will leave now. We have one final request. We'll all step out to take a media shot. But before then, I want to thank all of you for genuine dedication and commitment to this project, for traveling all the way, for responding to all my requests. To our team members, co-PIs, students, postdocs, outreach coordinators, industry practitioners, to our advisory board, to NASA leadership team for being around through the past 4 years. And I just kind of recalled what my grandparents told me when I was a small kid, that if you remain genuinely curious about developments in the world and treat people nicely, you will be the richest person in the world. Today I felt that I'm the richest person in the world. Thank you all.
Okay, so a final request that I have is, I think all of us will follow Rachel and we will go out and do that media shot right now, okay?